Okay, so here we are. We're looking at number 5. This was the differential equations problem. So we'll go and take a look at this. And the first thing that we're asked to do, part A, is to find a limit as x approaches 0 of f of x plus 1 divided by sine x. And we're taking limits, and there's no algebraic way out. So the way we're going to have to work this is with L'Hopital's. And what I want to point out, it's kind of important here, so I'll even put a little red star, is that to use L'Hopital's now, we have to justify its use. And that means that we must separately look at the limit of the numerator, and we separately look at the limit of the denominator. So when we go to the numerator, the limit as x approaches 0, f of 0 is -1 plus 1, that's 0. And denominator, it's a direct substitution, sine 0, which is 0. So what we are getting here is 0 divided by 0. That justifies L'Hopital's. We also know that had we gotten an infinity over infinity, that would also have justified the use of L'Hopital's. So what's different here? Separate limit calculations. If you want the full credit for any problem that involves L'Hopital's, you must show the two separate limits, numerator, denominator, then draw your conclusion from there. So now let's go back and finish this up. We know that we use L'Hopital's means we take the derivatives, numerator and denominator. So we're looking now at the limit x approaches 0 of f prime of x, and then 1 goes to 0, divided by derivative of sine, cosine of x. In order to figure out the derivative of f at 0, we have to come back up here and realize that we are given the derivative of the function. We're not given the function, but we are given its derivative. So in order to evaluate the derivative, we know x is 0, but do we know y? Well, it turns out that we do, because f of 0, or y, is equal to -1. So when we go ahead and substitute this derivative, it's going to be y squared 2x plus 2. And this is going to be a cosine 0, which is just 1. Move this down here. So y is -1. So this is -1 squared. 2 times 0 plus 2, that's 2, divided by 1. And this is going to be 2. So the answer to part A there is 2. We go to B. B says use Euler's method. And so if we go ahead and look at Euler's method, it says start at x equals 0, 2 steps, getting f of 1/2. So we're going from x equals 0 to x equals 1/2. And we do our little table here. We're going to start at 0. We're going to go 1 step, 2 steps, and end up at 1/2. That puts us midway at 1/4. So our delta x is 1/4. We need our y values. We know that the y value for 0, we already had that, was -1. We're going to need to calculate the next 2. And we're going to do this by evaluating the next y. And we use the Euler's method, which is basically just the tangent line. So we're going to write down that the new y is going to equal the slope, but the slope we have is y squared 2x plus 2, that's our dy dx, that's our slope, times the delta x plus the older y. So this would be y2, and this would be y1, and this would be x1. So this is what we're going to use to calculate our values. Now it's just a matter of kind of stepping ourselves through. So with 0, -1, the new y is going to equal this slope value, which we just did up here. This is 2 times the delta x, which is 1/4, plus the current y, which is -1. And when we evaluate this, we get -1/2. That's the next y. So we're going to do this again. The new y is going to equal, we need y squared, so that's 1/4, twice the x plus 2. So twice 1/4 is 1/2. 1/2 plus the 2, that's the slope. The delta x is 1/4, and add in the y minus a half. It's a little bit of an annoying calculation, but this is a negative 11 over 32, and that's actually the answer we wanted. So that's the value from Euler's method. And finally, we go to part C, which asks us to solve the differential equation itself, given the initial condition that f of 0 is equal to negative 1. So if we take a look and go recopy the original equation, dy dx equals dy dx is equal to y squared 2x plus 2. Basic plan, multiply up by the dx, put the x's together, take the y squared, and that's going to come down here. So that leads us to a dy over y squared equals 2x plus 2 dx. And most of you did seem to have this part okay. I'd rewrite this with power rule as y to the negative 2 dy. We're going to then integrate both sides here. The integral of y to the negative 2 dy, add 1, so we get y to the negative 1 over negative 1, so negative this, equals this antiderivative, pretty straightforward, x squared plus 2x. We'll throw our plus c in on the right-hand side. So we're just solving this for first c and then solving it for y. This is negative 1 over y plus 2x plus c. We know that f of 0 or y of 0 is equal to negative 1. When we substitute in all these things, y is negative 1. So we get negative 1 over negative 1, which is just 1. All the x's are zeros. It looks like c is 1. So we're at now negative 1 over y equals x squared plus 2x plus 1. That's our c value. I'm going to take the reciprocal of both sides. And then finally multiply by the negative. And so we get y equals negative 1 over x squared plus 2x plus 1. And that's a good place to stop. If you recognize the denominator as x plus 1 quantity squared, you could certainly rewrite it that way as well. And that's going to be it for problem 5. I posted solutions to the other problems, but they're not me, they're somebody else, but does go through them as well. See you Monday morning.